Well, I think we're ready to get started if the rest of the people want to come in and take their seats. And thank you all for coming. I want to welcome you on behalf of the Computer Museum History Center. I'm John Toole, the Executive Director and CEO, and I want to give you just a couple of minutes introduction about the museum and where we are, and some new material that I think you're going to enjoy before I introduce our speaker. Obviously, our roots started up in the Boston area over 20 years ago. Gwen Gordon Bell had this dream of really preserving the artifacts and stories of the information age and developed a world-class collection. That's where we start from. And we've really moved it out here to Silicon Valley, beginning in 1996, have doubled it in size, shape, and junk, if you will. But it's the junk of really what really makes the difference, to preserve what this particular wonderful period has been all about. And that's what sort of the theme of really tonight's all about, with Dan Ingalls talking about some of the great things that emerged right here over a long period of time. Our collection covers not just the hardware artifacts, software, photographs, documentation, thousands of those kind of things. We're putting together into really an international class museum that we hope to be operational in 2005, break ground in 2003. And I want to tell you a little bit about how that all works. Some of our collection, some of you have seen it. We normally have a great reception afterwards with wine and cheese. Dan, we'll have to invite you back afterwards for something. We're here at Xerox PART, so we're not going to be able to show you our visible storage area this evening. But I'm going to show you a couple of little things of parts of our collection that some of you may not have, that those of you have not been to. So you can see some of these artifacts up close and personal right now. This isn't our museum. This is really the part of the dream of what you can see, some of these machines, some of the software pieces that were made possible by those machines, and the way you can walk through and see what's all happening. This is just a view of an IBM 36090. As you walk down to the right, there's all kinds of unit record equipment. We've got some crazier things. That little red thing in the middle is a kitchen computer made by Honeywell. A few that were made by Honeywell with a 316 standard machine, of course, which was later used for internet IMPs. But in this case, this was to feed recipes in a kitchen that cost $10,600. You may have read about it in a New York Times article about us. In fact, if you watch the Wall Street Journal on Monday, there's a possibility of another article coming out on us. This is another great shot. If you look down at the end, you don't have to put your magnifying glasses on. At the end of that tunnel, if you will, is Gene Amdahl's whisk machine in 1952 that he did his PhD dissertation on. Gene was one of our featured speakers at our lecture series several weeks ago. And to the left is an IBM Stretch, and to the right you can start to see some of the evolution of what Seymour Cray and some of his first machines were. The Johnniac, one of a kind, that was almost lost in a LA County Museum parking lot that was thrown out. Fortunately, Willis Ware, Keith Ungerfer saw it. They called the museum in Boston. It was shipped back to Boston. They sent a team to restore it. And this is part of what our mission is to ensure that some of this rich history can be put together in a cultural institution that's really going to make a difference for the world. Again, there's the pictures of some Crays, some of the supercomputers, and of course, as we get down, there's a whole deck collection because Ken Olsen was one of the earliest founders of the museum, and we have a PDP-1, as you can see, which we're probably going to take on as part of our restoration project in the future with all the PDPs, you name it, that go down that hall. This is an IBM 1620 that was actually restored by a team of volunteers. I mean, volunteers are really, really critical, by the way, many of which are in the audience, many of which are outside helping us, and I think that's what really makes things vibrant overall from the museum perspective. Come see this demonstrated sometime. And of course, we have a wall of PCs, okay? And this is where this little machine that Dan will talk about resides, or at least not right this second, okay? But really the whole history of many of the things that went on. When the IBM PC, of course, in 1981, was featured as the birth of the PC, there were many other things that happened before it and after it and through that period of time. And that's, you can come and see up close and personal all that kind of history that we really want to make into a grand institution. And in addition, we have a special exhibit there that we did with the Intel Museum that features artifacts, a little bit more curated kind of things together, because we're a mixture right now of, you can see some of these artifacts at the same time. you can see what some of the lessons are learned. So I invite you all to come and see us in that particular venue. And we have a program with volunteers, an active board. Some of our board members are here, John Schock, Bernard Poteau. Any other board members here? I think Eric Hahn was going to be coming this evening. People that are really care about computing and the information age and preserving the artifacts and stories that we have. We're part, and what's really exciting is a complete proposed NASA research park at NASA Ames. We ourselves are an independent nonprofit organization. So if you donate money, you can take tax deductions in the United States, by the way. But we have an international in scope, and what we're putting together at NASA is a complete park. The big hangar is going to be converted into an Air and Space Center. We've got 3 acres of land in front of that Air and Space Center, that hangar right now, that we're going to build a building of about 114,000 square feet. Across the street, we'll have a university complex. You see Santa Cruz, Carnegie Mellon, a few of the other universities, and then around it will be a research area from Lockheed Martin and some other folks that are going to be building some work that will be working with NASA. So all together, we're going to be part of that, and this kind of gives you a breakout. Where are we now? People always want to know, are we, is this just pie in the sky? Are these just PowerPoint briefing slides? Having spent, 10 or 15 years at ARPA in my previous life, Dan, I know what briefing slides are all about, too. The answer is we've made tremendous solid progress in the last couple of years. In the past year, we picked our architect team. We picked our exhibit design team. We're putting that together. We're going to be putting a groundbreaking in 2003. We're going to be operational in 2005. And in the meantime, we're going to be building an interim facility just to consolidate some of our people, our exhibit space, and give some additional capability for our storage space. That's going to be operational in June 2002. So hopefully, and the other good news, by the way, is the actual security gate, which is a little bit of a difficulty coming and going for much of us in the public sector, is going to be moved in January. So this will all be open space. Okay, so we expect to have kind of a real revolution, if you will, of many different kinds beginning the next calendar year. That's our site. That's one of 9 or 10 different ideas that came up in an ideas competition, one that was submitted by EHDD, our architect that we chose. This is kind of a facility rendering of our interim facility. And I guess what I want to welcome everyone again is just to enjoy the programs that we have. We have a tremendous lecture series. We have Gene Amdahl. We've had Linus Torvalds. I'm sorry, I'm standing in front, but I can wander a little bit, but I want to get back to my thing, my slides. And of course, Dan Ingalls this evening that I'll introduce in just a few minutes. And of course, coming up, really our signature event every year is the Fellows Awards. This year we're honoring Fred Brooks, Gene Samet, and Morris Wilkes, okay, as 3 new fellows. So we're really honored that, and that's October 23rd at the Fairmont Hotel in San Jose. And I guess last but not least, I urge you all to get involved as you can with us. People make it happen, spread the word, help us spread the word about what we are, what we're going to become, because you're the ones that are going to make it happen. Volunteer where you can, and of course, become a supporter. Tonight, tomorrow, yesterday, whatever, because it takes a lot of energy, people's time, and things to make this happen, both financially as well as blood, sweat, and tears. So with that, I'm going to go back, and I just want to say a few things about Dan Ingalls, but I know everyone here tonight came because they probably already know. I was telling Dan before, when I think one of my first days at ARPA in the 80s, I saw Alan Kay's Dynabook picture that was, of course, had done even well before that, the vision of what the future could be. And I just recently learned of how fundamental the Smalltalk era was really all about, to really implement that type of vision in many different ways. And of course, I think Dan's taken not only 5 generations of Smalltalk and different kinds of architectures to Squeak, which we're going to hear about tonight, and how that evolved, but literally the whole magnitude of being countercultural, being revolutionary, and being Dan really makes a difference. Because I think those are the kind of things that have really made progress in innovation. And with that, I'm not going to say anything more, Dan, if I may, but let's please welcome Dan Ingalls for an evening tonight. Thank you.
being Dan was the easy part.
Plugging you in, maybe the hard part.
Oh, yeah, that's right. Thanks. Yeah. That's great. Don't want to tell you how many times that hasn't worked. Yeah, right. It's really great to see everybody here. It's I can't think of a more fun group to have at a party, so thanks for coming. Plus, as was pointed out, I think we have assembled here people from just about every generation of Smalltalk and Squeak, so if I forget to say something, you can help me out a little. I feel really lucky in the time that I've spent on this stuff, just to have, been in the right place at the right time. It's hard to take credit for what went on, just because it all seemed like stuff that was just waiting to happen. The one thing that I want to really acknowledge, being especially in this room, is the enormous support of the Xerox Corporation in the early days. And I started out with this slide. I wasn't thinking about Xerox, but this slide shows the scientific method, where you make an observation, and then based on that observation, you formulate a theory, and then given the theory, you propose an experiment, design an experiment to test it, and then you make an observation. And you proceed through that cycle, and you learn more and more about what you're doing. And over time, it became clear to me that that's what we were doing with the design of computer systems. We'd build a bunch of applications using whatever we could, and then we'd see all the things that were wrong with them, or it seemed sort of too verbose or not general enough. And out of that would come the notion of some sort of better language for describing what we wanted to do. And the form of experiment in that space is building a system using that language. And then you use that system to try to do all your applications, and you're back learning more about it. So the acknowledgement for the Xerox Corporation is that they really gave us the time, the space, the money to do that. And also I have to acknowledge Alan Kay, that he really, he has an enormous commitment at this level to let that process go on and pay attention to what's learned. So I'm going to go through a bunch of generations of Smalltalk that at least I had something to do with, and just talk about it. I gave a talk a little bit related to this at Stanford that sort of went into a lot of technical details, so I'll probably not do so much of that here, and maybe tell a few more stories or something like that. And hopefully I'll get through most of it in about half an hour, 40 minutes, and then I've got some sort of a tour through the Squeak system at the end, which is our latest turn around this circle. I wanted to start by talking a little bit about what were the most important influencing factors going into Smalltalk for me. So the first one was Lisp, and Lisp is this, at least at that time, this utterly simple and utterly general system. And you could type in these sort of structural expressions and get them evaluated. And there wasn't anything you couldn't model that way. So most of the Lisp programs kind of look this way. And I think the thing that I thought was so great about that was that in addition to its complete generality, underneath the system you had automatic storage management. So all these structures that you created, it was like you could create these things in air, but they got kept for you. And you could sort of make them behave just by mentioning them. And so this here is setting up a list and defining something that will compute the length of a list, and then running it on that list. The place where it fell short in my experience of the thing that I wanted to have and live with was just that it was, the user experience at that time was that it was sort of too symbolic, kind of not enough help from the syntax, and sort of you had to always be imputing the structure of what you were working with. But Lisp to me was sort of the strongest, base influence. APL I really liked, and Ted started working with us, and he had loved APL. And APL had sort of the additional structure, the additional syntax that made for sort of a lot of real terseness. The only thing was that it was mainly about arrays and numbers. So it had a whole bunch of neat little functions for working with arrays and numbers. And it had the polymorphic experience to it because there was a lot of uniformity in how the functions sort of behaved on all the different structures. And you could do these little real simple one-liners, like this thing here is a multiplication table just done in one simple statement. And it had that same quality that the Lisp systems did of just printing back the value to you. It's like having a handheld calculator, but with a whole huge computer behind it. So we really liked that sort of terseness. And I got interested in that. Let's see. At the time I came to Xerox PARC, I came to work on speech recognition. And Ted worked with me on that also. And we spent a lot of our time working in Fortran, trying to, do fast Fourier transforms on speech. And we were thinking of APL, and I was beginning to think, gee, maybe we could build an APL, and then we could do all our speech recognition in that. And then we wound up in an office across from Alan Kay's, and I pretty soon realized that I was more interested in the conversations I heard across the hall than I was in speech recognition. But anyway, I talked to him about my enthusiasm for APL, and he mentioned another language called PPL, which is a polymorphic programming language done by Ben Wegbright. And so I got all excited about that, and I thought, oh, that'd be great. And what that added was it sort of gave you the terseness and other nice features of APL, but in addition, you could define your own data types. And then Alan talked about the problem with most extensible languages, which is that if you have a bunch of parts in an extensible language and you keep adding new things to it, then it starts being the case that the routines that you have, the functions that you work with, start to get more and more complicated because they have to test all the cases of what different data types you're working with. And it's not only do things get more complicated, but for instance, supposing there's something that will print anything in the system, and you come along and add a new kind of a thing, like a vehicle. Then you want to be able to print the vehicle. So here you go, and you have to edit the print routine. And this is terrible because you're editing a system function, and if you make one false move, the whole system will break. So fragility is another problem with a lot of extensible languages. But the real problem is this n-squared problem. This shows if you've got 6 parts to it, then there are 36 sort of interdependencies that are possible. And as you start making a bigger and bigger system, if you grow an extensible language, it just gets more and more complicated. So that's only about 25 nodes, and you can see that now it's all about the cross-dependencies. So that had been kind of a limitation of extensible languages. And the one real sort of key influence that I never experienced, but I got it, Alan had read about it and described it to me, was the notion of classes and instances in Simula, which associated all the procedures for dealing with new data types with the class of the data type. And it offered a real picture of how to go forward without this n-squared problem of extensible languages. And the last one was Meta 2. There were a whole bunch of systems called Meta. Meta 2 is the one that I love. And if you haven't ever read this paper and you're into computers, I highly recommend reading it. It's called Meta 2, a syntax-oriented compiler writing language by Val Shorey. And it came out in 1962. And it's, let me. So in that paper, you won't be able to read this, but this is a simple little version of something that compiles a small sort of a subset of Algol into machine code. And what's neat about it is that, let me bring that out where I can see it, or you won't be able to read this, but I'll just go through it. And so these little statements here, actually, this says a program is a block, and then you go up here and you see the definition for a block. And a block is, and then it says begin in quotes, and then it checks for declarations and any number of statements. And you go down to statement and you see that it goes through that. And next to each of the places where there's something like begin, which is testing what's coming in the program, there's another little statement that has to do with outputting. So this just made it incredibly simple to write something that translates from one form to another, such as from a simple Algol program to an assembly code program. And let me shrink that one down. What I love about this, I feel I owe it to Val Shorey to proselytize a bit about it. And this really, I think it influenced what we did. This is the meta program that does that transformation, compiling itself. So this whole thing that sits there in about 20 lines of code is this meta compiler. And so you can walk up to this, and this is what fascinated me about it. The only system I had to work with when I first got to Xerox was Fortran. That's because we had to do this speech recognition on a Sigma 3, and that was all that we had there. This Sigma 3 was, let's see, a machine sort of the size of a small kitchen that's about the same power as a Palm Pilot, I think. Anyway, just by rewriting this one little thing, you can then translate this meta compiler into, say, Fortran or whatever you've got, and then you've got a compiler that you have control over. So I guess that was another thing that was so neat about meta, is that it was clear that it was one of these systems that sort of gave you control over your universe. So those were the Lisp, APL, Simula, and Meta were the ingredients that I thought were important. And Alan agrees with this pretty much, although really, to get his perspective on it, you should read his paper in the History of Programming Languages. So let's see. We were trying to, this was in the summer of '72, I guess. Ted and I had been working on speech recognition. Then we were working with Alan, and we asked him one time, how big a system, he thought it would have to be really a great system. And he came back with, a sort of a quick comment of, well, a page or less. and so we said, yeah, prove it. So he went away for about a week and kept coming back, every day or two just to try stuff out on us, and came up with really a way of doing this language, which became Smalltalk 72. And the notion is pretty simple. You take an expression such as 3 + 4, and you split it up so that what it means is that you are sending the message +4 to an object 3. And what's neat about this is that all of the control for what gets done is in the receiver of the message, and it then suggests building an entire system that way. So here's a real simple example defining a pair like a pair in Lisp that consists of a head and a tail. And this is sort of all the code you need to get the basics of Lisp working. And here's how it works. This little program says, well, if it's a new pair, then set the head to be colon. And what colon meant was go out and evaluate the next thing in the incoming message. And then set the tail to be the next thing in the message. So you've there described enough to make an assignment like this, which says set A to be a pair of 3 and 1. So that's all described here. And then here are a couple of other messages you can send to it. You can ask it for its head. This little eyeball means look in the message stream and see if there's the token called head. And if you do see that, then look for an assignment arrow. And if you see that, then pick up the next thing in the message stream here and put it in the head. And if you don't see an assignment arrow, then it must be asking for the value and return that. So that's how Smalltalk 72 worked. And this would allow you to create these pairs, to store values into them, to ask for their parts, and this little thing down here will print it. And Alan called it an extensible language with intrinsic semantics, which I always thought was a great way of talking about it. You could add any amount of data types that you wanted, so it was extensible. And intrinsic semantics meant that the semantics of the language resided in the objects that were being used. And sort of from Lisp came this notion of a simple eval, simple evaluator, and automatic storage management. From APL, we got sort of the simplicity of infix and some helpful syntax, because you could make whatever you wanted be the syntax. From Simula, we had classes and instances. And from Meta, this notion of gobbling up a message stream. Only we weren't just outputting stuff, we're actually running it. So the people who gathered together to work on this included Adele Goldberg, this is in alphabetical order, me, Chris Jeffers, Ted Kaler, who's here, Alan Kay, Diana Mary, Steve Purcell, John Schock, and Bob Shore, and let's see, yeah, those were most of the people. And this is, when Alan came in with that sort of, it was actually less than a page evaluator, then we talked about it more, and he did an iterative version, like the iterative version of the Lisp interpreter. And this is, it was really about a page and a half. And this is sort of after our conversations, this is the pseudocode that I worked from. I actually wrote this from the Nova code to build the first interpreter. And let me go on here. This is a diagram. I'm not going to get into the sort of bits and bytes of how this worked, but I know Don Knuth came here, and I want to really acknowledge him. This was, once we had that, there wasn't any other system that I really had to implement it in. And so, well, actually, so, excuse me, in terms of history, I implemented that in BASIC the first time around, and I think it's, I don't feel apologetic for it. You use whatever you can to try something out the quickest you can, and at that time, I wanted to work at home because we had just had a child, and I had a link to a Nova machine here at Xerox PARC, and the only thing that it had running interactively on it was BASIC. Anyway, coming back to Don, we had to create this thing out of nothing. I mean, I had the BASIC program that showed that it would work. I think it took a couple of minutes to do 3 factorial. And so then transcribed it all to Nova assembler code. But the problem was that, there wasn't any storage management. So I got to learn all about storage allocators and first fit and best fit and all of that stuff, and reference counting. We used reference counting to manage storage in the first couple of Smalltalks because we wanted to have decent real-time behavior, and all the garbage collectors we had seen at that time had significant hiccups when they ran out of memory. And the machines we were working with were really small. These were 32K that we had to work with. So let me just go on here a little bit. I'm not going to go into the details of how all that worked. I will show you, I had, since this is a talk for the Computer History Museum, I had my fun with computer history. A couple of years ago for Alan's birthday, I did a version of Smalltalk 72 in Squeak. So let me just, hold on a second there. Let's see. Oh, I've really blown it here, folks. I tried that, yeah. Let's just try this here. Yeah, there we go. So what you're seeing here is the little text frame that we typed into in Smalltalk 72. So I managed we got a hold of the entire bootstrap of the Smalltalk 72 system. And so I just kept working on it until it would read that in and put in the primitives that we needed. So you can type in here things like, let's see, for I to 300 do. We had this object which you typed as an @ sign, and it was this little smiling face, and that represented a turtle like Seymour Papert's turtles in the logo project. If you tell me how that's working. Okay, so that's you could do these little turtle geometry examples, and you also let's see. I typed in that definition of pair, which is there, and so you could do things like set A to be pair of 1 and 2, create one, and then you could say things like a tail to get its part. So anyway, you can run all this, and it's kind of fun going back to it's fun to go back to a system like that and redo it, because in today's systems it's so easy. You know, you've got automatic storage management in the language itself already, and you can try out all sorts of things that just seem too difficult as experiments for us to do. So a bunch of things got done in Smalltalk 72, and we got a lot of experience with it. We certainly learned that automatic storage and dynamic types are kind of the key to object-oriented programming. Another thing that we learned was the way that we worked with the system on the Alto computers was that you could do what we called a snapshot, which is to save the entire state of your system on the disk. And this was really great because the Alto had removable disk packs. So when you walked up to an Alto and put your disk pack in, you were exactly back where you had last been the last time you worked on something. And that has stayed with us sort of throughout the Smalltalk project. We've always done systems that you kind of made changes in them and then got to a new place and could move on from there without having to wait the time to sort of take a long turnaround to regenerate things. You know, there are good and bad features of both approach, but that certainly kept, I think it added a certain liveliness to what we were doing. Another thing we learned was that turnaround time in research is much more important than speed. Of course, we had to, the system ran really slowly, I think about 1,000 tokens a second. So we had to have some rationale to feel good about a speed like that. And also, you can make up for speed with great primitives. So there were primitives in there. Diana Mary really worked really hard to get in decent support for text and for bit-aligned rectangle operations. And then Ted did, I think, the turtle line drawing. So with those things, we had a lot of fun and could do some pretty neat graphics, even though it wasn't the most powerful system at Park. We still frequently gave CSL a run for their money. Let's see. In Smalltalk 74 was the next system. You know, after a couple of years with this, and there were a bunch of significant applications that got built in Smalltalk 72, and a whole project with a school that Adele and Alan ran together. But we did want to make things go faster, and so Smalltalk 74 was an attempt to do that by we tried to clean it up by making an object for the incoming message stream that you could put all these special operators like the colon and the eyeball into and define them in the language itself. And we made a dictionary for each of the procedures. Is that helping? Uh-oh. But there were... and Dave Robson and Steve Wire came onto the project. And Dave did some special microcode for Smalltalk 74 that made it run a little bit faster. But still, it simply didn't go that fast because it was really spending a lot of its time doing parsing. Also, there were ambiguities. You could write things that were completely ambiguous in their syntax. And although people didn't try to do that, they would occasionally combine two systems, and you'd find out that there were ambiguities at that time. Also, activations, which is the equivalent of stack frames, and the classes in the language were not real objects in the language. So we had some forward distance that we still needed to go with the language itself. But a great system was done in Smalltalk 74. So we're now 2 years down the road. And we were running out of space on the altos. And Ted and I designed this thing called Ooze. And it was a way of, we thought of doing just an object-oriented memory. But we were, just a virtual memory. But it looked like the behavior on the disk would simply be too fragmented, and and also things would be too fragmented in main memory if we did that, because we didn't have much space for paging. We've got 32K to work with, and we've got all of our interpreter, and it got down to a very small amount. So Ooze actually took, on a per object basis, packed everything into memory, and it zoned the disk by the classes of the objects. So it gave you a nice sort of approach for going for something on the disk and yet a really compact storage in memory. And it let us, if you work it out, we could have 65,000 objects, and that was enough to pretty much address the entire Alto disk. So we had it about as good as we could. And that served us for, another whole, like 2 or 3 years of work. And we also figured out BitBlit at that time. And let's see. So it was great to have had all this experience with text and with rectangles on the screen and with line drawing, because it started to suggest, we had about 20 pages of masking and shifting instructions. And the light began to go on that there must be something common at work here. And I guess the other thing was that at that time there was some room available in the Alto for more microcode. And so I really have to also acknowledge the whole Alto project and the other microcoded machines for a certain focus put on our work, because it's really valuable if you have a sort of a very limited resource that's 5 or 10 times faster than anything else, because it makes you look around for some common little thing that you could put in that place and make everything go faster. And so BitBlit was that. Basically, I sat down with Diana and all of her code, and I think Ted was there, and we started sifting through this. And the one thing that we were left with that was, we saw how we could sort of make a lot of stuff that was in common to all of that code. The one thing that was a mess was if you had to actually move something across on the same scan line in the display, then you had to be pulling out words, shifting them, aligning them, and putting them back all the way across. And the insight that I had that made BitBlit really work, I saw it visually as a wheel, sort of like a printing roller, like that. So if it rolled along, a bunch of words of image split up like that, then it would pick them up contiguously and could lay them down in the destination contiguously that way. And all you would have to do is mask at the edges. And then from there on, you're just loading full words and rotating this buffer. And the Alto was great at rotating. So that was something that we were able to contribute back to everybody at Xerox PARC. So then we got to do a new generation of Smalltalk. So we had Smalltalk 72 beefed up a little bit, and with this virtual memory and bitblit. And the only thing was that it was still incredibly slow. So Smalltalk 76 was another run at this. And I'm going to try and shorten things. Smalltalk 76 basically has everything in it that Smalltalk 80 did. Well, not as a language, but the virtual machine for it. So what it did was, in one fell swoop, it made classes and contexts, in other words, stack frames, be real objects in the language. It introduced inheritance amongst the classes. And it introduced keyword syntax that had a lot of the same nice kind of flexibility that the Smalltalk 72 syntax had, but it was a real syntax and it was compilable, and therefore also reliably readable by humans. And along with that, a compact and efficient byte-coded instruction set. So we figured out how to compile messages down to this, and with a lot of attention to efficiency. So things like plus got treated as special operations, except that we were very careful to make everything fail right so that you couldn't tell that it wasn't really sent as a nice message. And here again, we had the inspiration of microcode. That was what, again, made the sort of drive to have a bytecode engine, which was that, you know, you've got a machine that's 5 times faster than the memory available there to do all sorts of little things like instruction dispatch. So that all came together to make the Smalltalk 76 system, which was essentially the first and really is connected up to the very present day efficient Smalltalks. And let's see, people who had joined us by this time were Bob Flagle, Glenn Krasner worked a lot on the virtual machine, Dick Schaup, and Larry Tesler. And Larry really contributed a lot in that early time by he came up with the whole sort of pained browser notion that has stayed with Smalltalk for a long time and been picked up lots of places. The first Smalltalk system was really a nice small system. It consisted of 35 classes, 500 methods, and that all took up about 25K of code. And I wanted to show you that. I'm sort of partway through reviving that, but I don't really have it working enough to show. But it's a nice model for kind of how little you can get by with and actually have a decent development environment. This is how it worked, which I won't get into here. The next cycle that was useful for us was in 1978 we had the opportunity to build a real personal computer, and this is an example of one. It's the Notetaker, and it was done by Doug Fairbairn, and Larry Tesler helped out, and Bruce Horn also. And it was the first sort of thought that we had of, gee, this is something that could go out in the world and have an impact, because this was just the time when the Intel 8086 and the Motorola 68000 were coming out. There were 16-bit processors, and they really had enough power to do the kinds of things we were doing with the Alto. So this had in it an 8086. It actually had a couple of them. So what we did with that was this really taught us something, because we had to translate all of the system over to fit in an 8086. And so what we wanted to do was to get rid of most of we had, I think, 32K of interpreter code that ran Smalltalk at that point. And and we didn't want to have to rewrite it all. So this was the point at which we sort of decided to do all the graphics in terms of bitblit and get the kernel as small as we could. And we got it from 32K down to 6K of kernel code, and the rest was all in the high-level language, Smalltalk. And the thing actually ran Smalltalk twice as fast as the Alto. It didn't look quite as fast because the text display was not twice as fast as the Alto. Yeah?
One processor handling display, one processor doing the interpreting.
Not strictly. No, the display just, there was one processor devoted to the interpreter. There was also an Ethernet processor, and we did a cute hack, which was when we weren't using the Ethernet, which was most of the time, I had put a copy of bitblit in the Ethernet processor and a queue in between, so that we could have the Ethernet processor do the display of bitblit. And when you did that, it did run as fast as the Alto in text display. I think that's how it was there. So then, let me just say, since this is the history talk, I'll say a little bit about this. The Notetaker did not make it out into the world, and we were just getting more and more excited about Smalltalk, and more excited about the fact that these microprocessors were coming out on the market that were powerful enough, and so I think it actually helped that this died as a project, because it forced us to, want to put Smalltalk out in the world. And so there was, for the next 2 years, and let me also mention a couple of other people who came in the project. Jim Althoff did, Peter Deutsch, Steve Putz, and Trygve Reinskaug, who was a researcher from Norway and had a lot of sort of big application programs that he wanted to describe this way. Anyway, that forced us to go through the system, and Adele tied herself to the keyboard and documented the entire system. We also cleaned up several things. We made it be proper ASCII so that anybody could run it on any computer. We made a couple of improvements in the language, like block arguments and character types, things like that. So that became the Smalltalk that went out in the world and sort of established it as a real language. And it also had a user interface paradigm called MVC that Adele and Jim and Trygve Reinskaug especially worked on, and Larry's Paint browsers were implemented in that. So it made a pretty good development environment. And I was going to go through all that, but I think I'm just going to skip that and go to Squeak. So I left the industry for about 10 years in here. I went to Apple and got to do sort of another iteration on the Smalltalk 80 release. But then came back to Alan Kay's group in about 1995, I think, and joined up with a bunch of old friends. Well, Alan, Ted Kaler was there, and then also John Maloney had joined the group at that time. I was out of the group, so he had come along. And more recently, Andreas Raab and Kim Rose was a part of the group, and Scott Wallace, who had been with me at Apple. So when I came back, the group was sort of looking around for a software system to use for the next thing to do in the educational stuff that we wanted to do. And we sort of wanted a Smalltalk, but we didn't have one available. We had the Alto Smalltalk, the Apple Smalltalk 80, but it was all written in Motorola 68000 code, and by this time we were on to other processors, so that was a dead end. And we came up with this scheme to, we came up with this scheme to actually take a Smalltalk written in itself. The blue book that Adele and Dave and the whole group had published had in it all the code for a Smalltalk interpreter. So it occurred to us, gee, if we could just take that and translate it. See, the machines were much faster now than they were in those days. And the description of the Smalltalk interpreter that was in the books was put in there, and I remember this phrase when we put the books out, to debug the documentation. And I remember working with Dave actually getting it to run on the Xerox Dorado, which, gee, that was as fast as an iPac, I think. Anyway, so we went and somebody had actually, a friend of John's had actually typed in all the code from the book and gotten it to run, so that was available. We took that and ran it on an existing Smalltalk and could start doing the work we wanted to with the system. But what we did was we also wrote and John Maloney did this work, wrote a translator from the subset of Smalltalk in which the interpreter was written to C. So the way this kind of worked was we had a new CPU, namely the PowerPC at Apple, and let's see. Well, we had the old one that ran on the 68000. with a virtual machine and the Smalltalk image that ran on top of it. And sort of symbolically, what we did was we took all of the routines from the Smalltalk 80 text and ran them simulated in that system, and then wrote this translator to C. And then that produced code that we could put onto another processor, and in fact, any processor. So this is what really opened Smalltalk up for us in that process. And then from there, you could port the whole thing over and be operating on any machine. So this was the essence of the Squeak sort of scheme. And we then released that to the world, and making it a completely open and portable Smalltalk that's written in itself. So when you get the Squeak system, you get not only a working practical Smalltalk, but in it is the entire virtual machine written in that same language that you must know if you got it. And you can take it and do anything you want with it. So it's a nice system to have because you have sort of complete control over your software destiny once you have it. We've done a lot of things in Squeak, and I'll show you a few of them, but I'll just talk about the important areas that we extended. We extended BitBlit to color and also added what we call a warp drive to it, which is to allow it to scale and rotate and do anti-aliasing. We put a new sort of user interface paradigm on it, well, graphical display paradigm called Morphic that John had worked on when he was in the Self group. There's support for music in here, and this little bell, and there's somebody I've left off of this list that worked with us on music, and it's Steve Saunders, and he's here actually. So we've done more of that work. One of the neat things about this translation paradigm was, in addition to being able to make a fast, practical virtual machine from out of the language itself, anything that you describe in that same way, such as musical synthesis algorithms, can also be made into fast primitive operations. A lot of work on network support, sockets, and there's actually in Squeak an email system, a network browser, and a system for doing dynamic updates, which has really been neat for us in the open source community. If we come up with a bug fix, we put it out on a server, and every Squeak has in it the ability to go out on that server and see if there's been anything since the last time you looked, and if so, it files it in for you. So there are about 1,000 people on the Squeak list, but there are probably 50 or so who are really active and like to follow right along and help us fix bugs. And they're, with this mechanism, they're within a day of us in terms of the state of their systems. A whole eToy environment that I'm not going to talk about, but it's pretty neat, and if you see Alan's talks, you'll find out about it. It's kind of a layer on top of Smalltalk that lets you that lets you program with tiles and also interact with objects really concretely. There's also 3D support, and then just as the commercial Smalltalks have gone to doing dynamic translation for super fast interpreters, there's a project also with Squeak to do that same thing. We haven't yet managed to do that in Smalltalk itself, but someday we will. So let me come out and just take a quick tour around the Squeak environment itself so you get a sense of it. Here's just as an example of some text support. This is a paper that we wrote that if you want to read all about how we did Squeak, it's called Back to the Future. And this text is actually being displayed in with Squeak, and you can type and make changes, and the text all flows the way you'd expect in a Microsoft Word kind of processor. You can take graphical objects in and drop them down in the text, and this you can take it and rotate it, and the text all flows around it. So there's some depth to what we've got there. Here's when I worked pretty hard to make that stuff work, and there was also something I had always wanted to play with text. So this is some text within an arbitrary outline, and I wanted to be able to make that change with the outline. But also, there's text such as you can do in Illustrator that goes along a line like that, and I wanted to be able to sort of tie these things up together. So you can make chain text, and see here, if I change, I don't know if you can see it, but what's happening here is as I change this top container, it's sort of, the text dribbles out and goes through that drain pipe and down into the bottom. And you can actually, you can do all this, you can do this stuff dynamically. This is sort of viscosity seen in text. There's also support for sound here. I hope my machine didn't go to sleep on me. Let's see. Boop. Looks like it worked. So you can record out of the computer itself. You can. Uh-oh. How did we not do that? That's too bad. Okay. So you can record sounds. You can edit them. I'll just show you what you can see. And I'll also, let's see. So this is a picture of the sound, and you can play around on the keyboard with the sound. I don't know if you can.
You have sound there. You just hold your microphone to it.
Oh, yeah, that's a good idea. Let me. Good. But what I got to do? There's something. Let's see. Can you pick up this microphone back in the booth? Is that coming out there? Oh yeah, yeah, a little bit less. Good. So we should be able to trim this and have it just be that sound. Okay, so it missed. I'm going to take one more try at this, and then we'll move on to something else. Boop. And try trimming it. Okay, and then you can take that and show it as a waveform, and you can play around with this waveform and scroll around in it, see what it looks like. But you can also play it on a keyboard. So you can have all that fun that you'd like to be able to do. And I think the reason we focused on sound is that when we did the Smalltalk 80 release, it didn't have sound in it, and so all the systems that were done with Smalltalk 80 tend to be without sound. And it really, looking back, we realized if we had just done that, if we had just made that work, then people would be doing that kind of work in Smalltalk. So in Squeak, you can also, here's another pretty cool system that it's actually displaying waveforms in real time. But you can also go to a different display type, which will display the spectrum in real time. So for quite a long time, we had an FFT written in Squeak, but it ran pretty slowly. It was written very generally. And when Andreas Raab joined the group, he brought along a lot of expertise for fast floating point because he works with graphics. And he saw that routine, and he said, oh boy. So the next day, we had FFTs that were just able to do just about anything in real time. Let me show you another display that's even more fun. So John Maloney and I worked on this. So this is, let me move this guy out of the way. This is an actual sonogram in real time. So you can go do-do-do-do-do. Sort of see that. There we go. So you can go and play around with this kind of stuff and do speech recognition and bird recognition and whatever you want to do. I'll show you one more thing in the sound space that was a lot of fun. This is a thing that Alan put together, given all of this stuff that we had done. What it is, this here is a MIDI control panel that John did, and these are little graphical figures you can pick up and down for the players here. And Alan wrote these scripts. These scripts were done in this tile language that's been laid on top of Squeak. And this one here, let's see, this says, where's it good? Yeah, here's something that says, Claire Bear, that's the clarinet bear's scale factor, gets Claire Bear's scalar, and then, so basically, this is a little script which has hooked up the motion of this bear near and far to the slider in the MIDI control panel. Can you see that, the green one? Okay, and similarly, if I move him left and right, it changes his pan setting. And of course, there's something in there that changes his scale when you move him up and down. So this was sort of a nice iconic interface for, and then over here we've got a piano roll for the MIDI being played. So I can just play this. Oops. Okay. Can we get a little microphone here? And great. And then if I move this guy, more clarinet, less clarinet, you know. So you get the idea. And there's lots of other stuff in there too that I'm not going to take the time to show you. But for instance, there's a whole synthesizer patch controller here, and you can change the parameters on the voice, you know, up and down, and whoops, and then you can try stuff out as you make those changes. Whoops, let's see, let me go back to the I'm going to, let's see, how much time do we have here? Can I go another 10 minutes? Okay, great. I'm just going to go quickly through the graphics area because it'd be a shame not to. This is, I don't know, this here is just a neat little graphic that was done. It's simply a picture going by underneath some text that is a screen. And you know, you can type in it too, as you'd expect. And that was done with BitBlit. And here's the version of Bit. I said we added a warp drive to it, and here's a little demonstration of that. So this is something that's just looking at itself with the scale done by where the mouse is vertically, and with the rotation done with it horizontally. And you can have a lot of fun playing around with this. And then if you get down to the scale where it's where the scale is greater than 0, then it starts to magnify round off, and you get all these sort of neat fractal patterns. Anyway, that's just a demo of the stuff, and you'll see that that kind of support in lots of rotated and scaled things. Andreas came along though and did the job right with rotation. And so this is some true type text that's actually read into and displayed using his outline graphics. And if you take, it's probably hard for you to see just like that, but if I take a magnifying glass up and put it over there, you can see that that text is actually also translucent and displaying the stuff behind it. So it's really a nice job that he did on it. And I can show you that at work over here. This is a quick little cartoon sequence, and I can stop it. Let me stop it right there. So here's an example of a bitmap that's being scaled by BitBlit, and that's 41K right now. There's a little readout in the bottom that shows how big it is. So if I make it this big, it's already up to like 200K. Because it's 16 bits and lots of other stuff. If I take this guy out of the picture and pull him out, like that. There's a control I can get here that will also read its compressed size. So I'll put that up there. So it's just 1,500 bytes. And you can scale it to any size, and the edges stay smooth. So that's just sort of a demonstration of how nice it is to have that primitive support in the system. Then he went on to do a version of 3D, which I don't have a great demonstration of, but it inspired Jeff Pierce, who's a student of Randy Pausch's at Carnegie Mellon, on the Alice project to do a whole sort of 3D scripting system. So this is a simple little thing that is modeled after their work that lets people who don't know much about 3D do scripting in it. So that says bunny move forward, and then there's an undo button. And it has this nice notion of sequencing the time so things aren't overly sudden. And I'll just jump to my favorite example here, which is a little script that basically says, tell the bunny to watch where the cursor goes. And the last thing that I'm going to show with his work is actually a whole 3D environment. And this is all running in Squeak. And it runs much faster with his new accelerated stuff. And I just was unable to sort of combine that with this demo. But here we are coming into a room. And this is the whole crew that I work with and that did Squeak. And I think that's probably a good place to stop and entertain questions. Yeah.
Up to the microphone so that it would help the recording.
Give you some exercise, too.
Yeah.
And if anybody's reluctant, I'll hand you this. Oh, yeah, great, you can do that. Thanks. Yeah, questions?
Is it on?
Sounds that way.
Simple question. How much of this went into Cedar and Mesa?
I don't know that I'm the wrong person to ask. Is there somebody here from Cedar and or Mesa that sort of knows what came out of this? I can tell you one thing, BitBlit sure did, because there was. Yeah. So, well, yeah, but I don't know that you got that from us. You guys had worked with that. I gave a demo to CSL when we first got BitBlit going, and the next day, Smokey Wallace came into my office and said, "I want to talk to you about BitBlit." Any other questions here? Oh, come on. Or stories to share. Yeah, Elliot.
Why you wanted to make the whole system in itself, and why you wanted to use objects as much as you did?
Why we wanted to do the system in itself, and okay, well, the reason I wanted to do the system in itself, well, there were two reasons. One, which I did say, which is this ability to make things be cross-platform, although that really comes from the translation. There's an upside, and the downside of single language systems is that it may not be the best language, Squeak is not the best language for doing logic programming. But the wonderful thing about single language systems is that once somebody learns that language, they can explore everything. So that, I don't know if that's the answer that you had in mind, but what I love about the system is that somebody, if some student gets this, you think about new musical instruments and what's going to happen when a Beethoven gets a hold of them, then, you sort of want to make the computing environments available ready for the next, von Neumann or whoever to come along and do something incredible. And it really is the case now that any old student could get Squeak off the web and could keep digging and go as deep as he wanted to go into musical synthesis or go into the virtual machine and change it. So that was our interest in that direction. And let's see, the second part of your question was about all with objects?
Yeah. Say more about the psychology and paper but your take on that.
I don't have a big take on that. It works for me, I think would be the answer. Yeah.
that you mentioned in the mid-'70s or something like that. There were a couple of papers that made it seem like students were able to do prodigious things with Smalltalk. I don't know, there was 72 or 76 or something.
Yeah, it was using the Smalltalk 72
Was-
system.
Was that because they were prodigious students in the first place? Because Smalltalk was an incredible tool? Because they had incredible teachers out of Park to do that? And it seemed that it was an incredibly accessible tool for those students. And I'm not sure we've had anything since that. Is Squeak as accessible as Smalltalk 72 was, or does it have different goals? Or
We're trying to make it that way. The Squeak that you would typically, download isn't on the face of it at all that way. But it has a whole what's called eToy system in it, which is this tile-based scripting, which is pretty easy to teach. I don't think we're breaking new ground yet, and I think Alan would be the first to tell you that we've still got some distance to go here. But I think Squeak is a great environment for doing that kind of work. And for instance, the new morphic display architecture is really nice for making stuff simple. It's currently, one of the problems that we've always had is we move so fast, there's a lot of garbage that accumulates. And so there's a lot of cleanup that we have to do as well as the forward progress. But let's see, to go back to, I think with regards to the results of those early experiments, I think it was all the things you said. There was good teaching, there were good students, but there were also normal students. And I think for the time, they did some incredibly neat stuff because Smalltalk 72 was simple and did have, powerful primitives associated with it. It was sort of the first system that you could do kind of iconic graphics that way so easily in a language like that. Yeah?
Does the Notetaker there still run?
I asked the same question, and they said no. And I'm not surprised, because when we had 6 of them just built, we had trouble keeping more than one running. But Bruce Horn's in the room, and he was the one who got them all to go. So maybe if we can keep him a little late, we could bring this one back to life. Yeah.
So I thought it was really interesting to see in such a short period of time this progression of more than 20 years from the original Smalltalk 72 up to what we see now. I mean, you can see just how the qualitative difference. So where do you think, complete the other half of the picture? Where is it going from here? What would you like to see? And, where do you think the qualitative difference will be down 20 years from now? Is that the sort of thing?
So you think we're halfway there?
Yeah, I assume if you keep pushing forward like this, you're not happy yet, right? So
Yeah.
where's it going?
Well, one thing that I didn't show at all, and it's sort of it's one of the most exciting areas, is the whole, integration with the internet. I mean, I talked about it, but I just didn't have it together to put together real demos of that. And I don't know if you watched the medium of the presentation, but some of this was sort of stepping through these book-like objects, and other parts of it were going into these what we call projects. And we've already got it working that you can actually take these projects and put them out on the web, effectively like web pages, except that you need to have a Squeak plugin in your browser. So I would say the next important plateau for us to get to is something that's reliable and that the various software operating system manufacturers aren't thwarting once a month, where you can really put all of this content out on the web and work with it, because I think that's going to open up something really big, which would be like, sort of HyperCard with multimedia on the web and alive, I mean, one of the things that I've often said is I like about Squeak is it's in, most software, the average software you get sort of arrives dead on arrival. All it can do is what they let you do. And Squeak is just the opposite way. I mean, it is, you can do anything in it, and in fact, you usually have to beat it over the head to get it to only do what you want. So I think that would be real exciting, and we're working hard on that. And the other direction is we really don't feel like we've gotten to where we want to get to, and that was why I said, you think we're halfway, with making stuff easy for non-technical adults as well as kids. There's still a long way to go. Actually, it may be only a teeny way to go. We just haven't seen it yet. Yeah, Don.
Yeah, so Dan, earlier you said that Alan's first reaction to extensible languages was the fragility of the system. So and now you as you say, you can change this thing all the time. So when you change it, a lot of stuff is going to break. How do you avoid this kind of thing?
So well, I may not have articulated this well, but moving from a procedure kind of model to a message sending model is what makes the big difference there. Yeah, and I should have been clearer about that. You live with something for long enough and you start to take it all for granted. But if everything you do in the system is done by teaching this kind of thing how to behave, and maybe so you've got in integers you have how they print, and in rectangle you have how they print. If you come along and add some new kind of object, some new kind of data structure, and you teach it how to print, it's not interfering with anything else. Now, it is true that it will get sent the print message when you create one of these and ask it to print, but the worst that can happen, usually, is that somewhere down in your code you do something wrong. About the only thing that usually can happen in a message sending language is you end up with a message that's not understood, and that's usually a soft error. I don't know if I'm addressing your question.
A person can also redefine pair or integer or whatever.
Oh, you can definitely break things, yes. No, but see, the thing is, in the old architecture, you're forced to go into a place where it's dangerous. Now, it's possible to go into where it's dangerous here, but
What I meant was, the only way I could make tech reliable was by having everything filtered through me. But somehow you seem to have a system that works with distributed control.
well, I don't know. It comes back to it works for me. People do crash Squeak, but I think with the people you were working with tech maybe weren't prepared to deal with things going wrong. Most of the people who go in here and actually make that kind of changes are prepared for things to deal with things going wrong. But it's pretty robust. Yeah.
I got my hand up and I have the mic for some reason. So I just want to know when Smalltalk's going to really complete the circle, and when are we going to see a basic implementation in Smalltalk?
A basic written in Smalltalk or
yeah, and which basic would you target? Would it be the original Dartmouth basic or the latest morphs from Microsoft?
Well, that's classified. Yeah, Elliot.
There is a commercial basic written in Smalltalk.
That's right.
Actually, you know the details.
I don't.
Oh, it's done by Carl Gundel, and you can buy it, and it's
Yeah.
been on the market for years.
Yeah.
It's called Liberty Smalltalk.
Right. Liberty Basic.
Yeah. That's right. Yeah.
Okay, I've got the microphone
And you were
now.
only joking.
I'm going to an incredibly pretentious workshop at UPSLA on Sunday, set up by Dick Gabriel, which is the Feyerabend Reinventing Computing workshop, which comes from a lot of feelings of the kind of being a corporate whore experience that many of us have in being programmers, and sees as its remit no less than throwing away everything we've got wrong with computing and trying to do more. So if I was to channel for you at that workshop, what would you want me to take to that workshop?
I don't know that we've really invented computing yet. Smalltalk is a really great assembly language. Now, where do we go? I don't know. I'm not good at making sweeping statements. I just do stuff.
Can
Other
you tell us
questions?
some of the inside story of why the Notetaker never became a commercial Smalltalk machine or a commercial machine of any sort?
No. It was, things get complicated in corporations. It probably was the right thing to have happen. But I wasn't even privy to all of it. Actually, Larry got closer to it. But I don't, stuff happens. And the truth is, it made us get stuff out in a sort of more general way, yeah.
What is the size of the virtual machine in Squeak? And is it adoptable to mobile computing?
Oh, yeah. Now, that's a part of the demo that I never gave. But let's see, a couple of things. It depends. The virtual machine has lots of sort of control in it over, what is that? Oh, great. Yeah. So it runs on the iPac, and it runs, Yoshiki has it running on a little Sharp handheld. It runs on most of the little handhelds. And the way that we do that, I'll come back to your question about size, is we reduce the image size down to sort of just the development environment. So if I have here, you can run the virtual machine and the whole, essentially the whole development environment, browser, file list, change manager stuff in about 1 megabyte. But you sort of get some choice about it because in the translator that generates the C code, you have the choice as to whether to inline a lot of stuff. And then also there's the choice about whether to include lots of special things like the outline display, like 3D, and so on. So typically when you do something for a little machine like the iPac, then you strip that stuff. Actually, the iPac isn't little, but like one of the, we had it running on the Cassiopeia for a while, the early one even. And there you strip a lot of stuff out. Yeah.
Concerning the Notetaker, all is not lost. That form factor probably inspired one Z80 machine, which I believe was the K-Pro, and that in turn inspired the compact luggables, which went on to make compact, and then after a long time, compact rescued deck, tandem, and etc. And now,
yeah. And there was also the Osborne, which is a similar.
And killed the Alpha, by the way.
Yeah, right.
Larry stepped out, but Larry has a whole story about Adam Osborne visiting at Park.
Oh, good.
And potentially seeing photographs of that machine before he did the Osborne.
Yeah.
But you need to get the story from Larry.
Yeah. Over there.
About efforts to make Squeak more approachable to novices, things like that. My experience downloading Squeak, I think like after Apple ATG posted it publicly, because I got into computers after the Macintosh user interface paradigms were there, having the scroll bars pop up on the left side of the field and disappear if you don't hit them exactly and stuff like that. There are various user interface paradigms that Smalltalk and Squeak had from before, the Macintosh and Windows type user interface paradigms, and now we have millions and millions more people who know these other paradigms. Is one of the things you're working on to try to bring the more well-known paradigms back to Squeak, or what are your thoughts on that?
Well, that's certainly something that needs to be addressed for certain audiences, but it's not what we're working on. I think there are people who are working on that. A number of people on the Squeak list outside have done systems just like what you're saying, and complete other looks and looks that are more like Windows and scroll bars. It's actually a preference in here, which side the scroll bar goes on, and which side it flops out, and whether they flop out or not. So, yeah.
Yeah, considering that you and Alan Kay were both at Apple, how is it they still have the scroll bars on the wrong side? I mean, they didn't get their money's worth from having you guys there, or what?
Well, let's see. Larry could tell you that. Yeah.
really bridging so many different generations that you have. So many different generations of Smalltalk. What were your best and worst times in terms of motivating yourself as a developer?
Well, there have been a couple of magical times. Every once in a while, you sort of see how everything could fit together, and then it's wonderful because no matter who's working on the project, if you're stuck on anything, you always have the answer. And doing Smalltalk 76 was one of those. We just sort of saw how it would all work, and we just coded up a storm. And I didn't get the timeline for that project, but in basically 7 months, we did this entire new generation with a new compiler, with a new virtual machine design, and had it all working at the end of that time. And then also with the thing with Squeak, seeing that we could take everything out of the book, actually get it running simulated, be working on it, be writing the translator, and have it all come together. And that was even less time because we were lucky because Mario had keyed in the whole interpreter. But so every once in a while you see things clearly, and then it's incredibly exciting, it's incredibly fun, you're never stressed out. And then the only hard thing is that you have to also be willing to sit around for 2 years waiting for that to happen, I don't know how you turn it on.
Right. Why don't we take one last one?
We had 2 hands. Let's take 2.
Okay, Dan, this is what I want.
This is Bruce Horn.
Well, I'm kind of disappointed with the systems that we have now because they're flaky and they only do what they can do, like you say, they're dead on arrival. So I want this system where I can boot right into Squeak and where you have kind of application modules. So if people write code that doesn't work, it crashes in their own little app. And I just want to have a Squeak environment that is, something I can use instead of Windows or OS 10 or something like that. And that would be something that would really, I think, would make a huge difference in kind of moving the whole industry forward because we're stuck with this static world, and I'm getting kind of tired of it personally. I'd love to see that, so I'll just put my 2 cents in for a vote on that for that direction.
Great. Yeah, me too. Yeah, one last one here.
Since this is a history lecture, I reviewed my notes and I noticed that after 1995, you didn't give any dates. Yet did Squeak, shall we say, reach fruition in 1995 and there's been nothing since then?
Oh.
Or was it a gradual process and what are some milestones along the way?
I'm glad you asked that. Very briefly, we put it out, was it in 96 that we put it out? Yeah. So we developed it during 1 year at Apple and had it ready to put out in the world by in October of 96. And that was incredibly fun because, we thought that it was going to be neat and cross-platform. In 3 weeks, Ian Pumarda, we just had it running on the Mac. In 3 weeks, Ian Pumarda, who lives in France, had implemented it on Unix. And in 2 more weeks, Andreas Raab in Germany had implemented it on Windows. I mean, you talk about the value of going open source. And then from that time on, yeah, I haven't put dates because I guess it's sort of too recent history. All the various things like the networking and the 3D, the outline graphics, the sound was there when we put it out. I'm not great about time. See, looking back far enough, I had to go to the sources, and they had, there were associated times. But does that give you some sense? So since that time, the last 5 years, there's been lots of activity in our group and in this whole open source community. Great. Yeah.
Dan, thanks so much for everything. What a great lecture. Here's a small token of our appreciation.
Thanks.
Dan will be around here for a little bit longer. He's going to be working on the Notetaker, and after they get it working, he's going to be programming out of it. Thanks again, Dan.
Thanks, you all, for coming.